Okay, so just want to make a point with a special kind of problem. Something that could make your life a little bit easier. So let's work out this problem. How many liters of CH4 at STP are required to completely react with 17.5 liters of O2? Just like the homework problems, nothing exciting. It's not a new kind of problem. Just want to make a point about something that may make your life easier. And there we've got CH4 plus 2O2 makes CO2 plus 2H2O. Okay. So, I start off by writing 17.5 liters of O2. Then asking myself some probably familiar questions. What unit do I want to get rid of? Liters of O2. Where's it got to go? On the bottom. What can I turn liters of O2 into? Moles of O2. Nothing different about that. Now, what unit do I want to get rid of? Moles of O2. Where's it got to go? On the bottom. What can I turn moles of O2 into? Well, moles of CH4. And my balanced equation says for every mole of CH4, I get 2 moles of O2. I need 2 moles of O2. Now, what unit do I want to get rid of? Moles of CH4. Where has it got to go? On the bottom. What can I turn moles of CH4 into? Liters of CH4. And if you push those buttons, you'll get 8.75. Hey, you can do it in your head because it's half of 17.5. Because look at the first and last conversion factors. Got 22.4 liters on the bottom. I got 22.4 liters on the top. Those will cancel out. And this is going to happen every single time you start with liters and end with liters. So wouldn't you like to be able to skip this step? Okay, but we have to justify it. Okay, I got to justify that I can just divide by 2. I got to justify that I need to change this instead of saying moles here. I need it to say liters. Does that make sense? I want this to say that 1 liter and 2 liter. Can I get away with it? Well, the answer is we can get away with it because of an Italian, Avogadro. Because Avogadro said equal volumes of gas at the same temperature and pressure contain equal numbers of molecules. The reason he's given credit for why the number's named after him, because he was the one that said, oh, it's important to think about how many pieces there are, and the easy way to count them is by the volume of gas. Because if I have 2 balloons, one has a liter of hydrogen, the other one has a liter of oxygen, they both have exactly the same number of particles as long as they're in the same room. Because the same room is going to be at the same temperature and the same pressure. Okay, so, well, how does this tie into what we're doing? Well, moles is the number of particles. Well, since equal moles are equal liters, I can treat my reaction as if they happen liters at a time. I can go from liters to liters. I can read my equation in liters as long as I don't change the temperature or the pressure. Now, with the example I gave you, it's going to be pretty easy not to change the temperature and pressure because I asked you about the reactants. But if I'd asked you about products, would it be reasonable to expect that the reactants and products would be at the same temperature when you're burning something? Well, not unless you wait for a while. You catch the gases and wait for a while. Does that make sense? So we can treat reactions as if they happen liters at a time. I can go from liters to liters. So on that big map I gave you, you can take a shortcut from liters to liters. Dave, for example, how many liters of CO2 at STP are produced by completely burning 17.5 liters of CH4? So notice this is not a different question because it's asking about CO2 instead of O2. But we're going to take a different approach to it. What do I want to get rid of? Liters of CH4. What can I turn liters into? I can turn it into moles and do it like I did the last time. But the last sentence says the temperature and pressure don't change, so I can go from liters to liters, taking the number out of the balanced equation. I can read that equation in liters because all the way up to the H2O. H2O is not always a gas. But 1 liter of CH4 and 2 liters of O2 will make 1 liter of CO2. Just like I could read it in moles. So 1 liter of CH4 for every liter of CO2. Hopefully you don't need a calculator to solve this. It has identity issues. Because one is the identity, yeah. Says same thing as moles because equal moles is equal liters. As long as they're both gases and the temperature doesn't change. Okay? So, on our diagram, we did this. Right? Everybody remember this from yesterday? So now, we just made a shortcut from there to there. And I'm going to use the equation to do it. Right? Get the numbers out of the equation. Yeah. Yeah, can we interpret our equations in particles? Could I write that as 2 molecules of CH4, or 1 molecule of CH4 and 2 molecules of oxygen make 1 molecule of CO2? Yeah, I can read because I can read it in particles, I can make that same skip in particles. You're exactly where I was going. It's okay to skip there too. Because we spent our time interpreting them in particles, didn't we? We did a couple of assignments where you had to interpret in particles. So we can go straight from particles to particles, liters to liters. We can't go grams to grams. Because equal grams is not equal numbers of particles. So that doesn't work. Okay, so we can take some shortcuts. You don't have to take the shortcuts. It'll work the long way. Just want to let you know those shortcuts are available to you. Okay? And I'm not going to hold you up against them and say, ooh, that's not allowed. Well, it is allowed because we can read those equations. Hey, so now it's time to yield. Oh, but we don't mean yield like the sign. We mean yield the way farmers use yield. Farmers use yield differently than car drivers, right? How does a farmer use yield? What's a farmer looking for? They're looking for what is their field yield? How many bushels they get per acre, right? How much they get. Okay? So yield is product. Yield is product. And there are 3 ways we talk about product. Scientists talk about product in 3 ways. So there are 3 kinds of yield. Remember, one of the interpretations of the arrow was yield? This and this yield, that and that. Yield is like make. So the first type, First type is called actual yield because it's how much you actually get. You do the reaction, you weigh the product. Oh, that's a pretty useful name, actual yield. How much did it actually weigh? Now, in your homework tonight, are they going to ask you to pour chemicals, mix them, and weigh them? No, they're not going to ask you to do that. So, how are you going to get actual yield on homework? They're going to have to tell you because they can't expect you to do the lab at home. So somewhere in the problem, they will discuss the amount of product made. And they're going to discuss it as this is how much, when it was done in the lab, this is how much was made. That's your actual yield. Okay. They got to give it to you. Okay, second type, theoretical yield. Every one that you have calculated so far is a theoretical yield. If every bit of this and this get used up, this is how much I'll make. In theory, this is how much I could make. If everything goes perfectly well, I will make this much stuff. The theoretical yield. And that's actually the most you should make. Because if everything goes perfectly, you make the most you can. If anything goes wrong, you make less than that. You like a reasonable way to look at it? So the theoretical yield should be bigger than the actual yield or the same size. Or if it's not, if the actual yield is bigger than the theoretical yield, what's in your dish is not what you think it is. That make sense? You got something that's not what you said it was going to be. Something happened with your reaction that you got too much product. That could be the wrong product or extra product, the second product. Okay? And the third kind of yield is a comparison of those two kinds of yields. It's actual yield divided by theoretical yield times 100%. You do this calculation all the time. Because you use actual, theoretical, and percent yield every time I hand back a test. You take what you actually got on the test, divided by what you could have theoretically gotten on the test. And that tells you your percentage on the test. It's not new math. It's just doing it with chemicals. It's like every percent you've ever figured out. Okay? So theoretical is the answer to a calculation problem. Actual is actually somebody has to actually weigh it. And percent is a comparison of it. Okay? So 6.8 grams of copper is produced when 3.2 grams of Al are reacted with excess copper 2 sulfate. Oh, let me be really nice. There. I wrote the balanced equation. That's aluminum plus copper 2 sulfate makes aluminum sulfate and copper. I've just told you the statement, now I got to ask some questions. There's no question to answer yet. It's coming. Question number 1. I get too many people copying. I want them thinking before I ask the question. So the question is, what is the actual yield? So are you supposed to go take some aluminum and put it in copper sulfate? No. So how are you going to get it? Well, look at the problem. What did they tell you about? They told you about copper and about aluminum. Aluminum's a reactant. It's not going to be a yield. Copper's a product. It's a yield. If you read the sentence, it says 6.78 grams of copper is produced. Not can be produced, is produced. Somebody did this. Does that make sense? So the actual yield is 6.78 grams of copper. They either have to give you the actual or the percent, one or the other. What's the theoretical yield? How much copper should you have made? Well, now I got to figure out if I used up that aluminum, how much copper would I make? So I start with the 3.92 grams of aluminum, the reactant, to figure out how much product I'm going to make. And I want to get rid of grams of aluminum and change that to moles of aluminum. So we're right back to the stoichiometry problems we've been doing for a couple of days. Stoichiometry answer is a theoretical one. So 1 mole of aluminum is 26.98 grams. Then change mole of aluminum to mole of a different chemical, and the chemical I want to choose is the one they told me about, copper. And the number in front of copper is 3, the number in front of Al is 2. Now I want to get rid of moles of copper. And moles of copper I can turn into grams of copper because 1 mole is 63.55 grams. I'll push those buttons on my calculator. 3.92 divided by 26.98 times 3 divided by 2 times 63.55. And I get, with 3 sig figs, 13.9. And my units are grams of copper. Because that's what I'm going to see pile up at the bottom of my dish. The aluminum sulfate is going to stay dissolved. So I could just do this and then filter it off, and I'd get, that's how I weigh my 6.78 grams of copper. Everybody know what the next question is? I couldn't fit on the screen. What's the percent yield? Yep, it's a measurement. You got it with the measurement, it's sig figs. It's for me. Let me answer it. Yeah. I'll get my hammer time. Okay, so percent equals actual over theoretical times 100%. And percent is going to be my unit. Actual was 6.78 grams of copper. Theoretical, 13.9 grams of copper times 100%. And that works out to be 48.8%. Did this go well? No, this did not go well. Something went wrong. What could it be? Well, we'll talk about why, because percent yields aren't always 100%. Okay? But here's a different one. So you got 48.9%, right? Or 48.8%. If you'd started with 9.73 grams of aluminum, how much copper would you expect? So now you know the actual, you know the, you can figure out, you know the percent, and you can figure out the theoretical. if you know the percent and can figure out the theoretical, then you'll be able to figure out how much the actual was. So if I had started with 9.73 grams of aluminum, I want to get rid of grams of aluminum, turn to moles of aluminum. 1 mole is 26.98. Oh, this should all be familiar because we just did it a second ago, right? Moles of aluminum to moles of copper. 3 moles of copper for every 2 moles of aluminum. Then moles of copper, grams of copper. 1 mole is 63.55 grams. So 9.73 divided by 26.98 times 3 divided by 2 times 63.55 equals 34.4 grams of copper. If I use more aluminum, I can expect more copper. Yeah. Okay. But that's my theoretical yield. I know that I'm only going to get 48.8% of that. Because I just did this lab. I get 48.8%. So am I going to get 34.4 grams of copper? No. What I'm going to get is 48.8% equals how much I'm actually going to get over 34.4 grams times 100%. Because I got my percent. That answers the theoretical. I can figure out the actual. Okay. First thing we do is divide both sides by 100%. That gets rid of the percents too, and I get 0.488. Doesn't have any units on this side. Move the decimal place over twice. Then multiply both sides by 34.4 grams. Move the decimal place over twice and multiply it by the theoretical amount. So 0.488 times 34.4. Gets me that my actual yield that I could expect would be 16.8 grams. Extra super hard? It's just a percent problem like you've been doing since, what, 5th grade? I think that's where they introduced percents. Okay. Percent's the same everywhere. Just it means out of 100 every time. Okay, so what does percent yield tell me? You want this person as your lab partner? Got 48.8%. Okay, percent yield tells us how efficient a reaction is. Ideally, we'd like to get 100% every time. It can't be bigger than 100%. Because if you get a percent yield bigger than 100%, that means you made more than you could possibly make. Which tells you that what's in the dish is not what you think it is. Does that make sense? Maybe a different reaction happened. Okay? Fact is, very often it's less than 100%. Why would it be less than 100%? Common reason? Somebody used lousy technique. They didn't transfer every drop. They didn't make sure they got every drop to move from point A to point B. You leave little crumbs behind, that reaction's not going to react with that. Spilled a little bit of powder before you reacted. Not waiting long enough for it to finish. Hey, even if you wait a long time though, that reaction may not go to completion. Oftentimes reactions end up at a place where they're not all the way completed, but they're reversible, so they're unhappening just as fast as they're happening. So it looks like it stopped moving because they're unhappening and happening at the same speed, but you haven't gotten rid of you haven't made all the product you could have. Side reactions use up the reactant. What do you mean by side reactions? Well, what if instead of that being copper 2 sulfate, it had been copper 1 sulfate? What if I had some copper 1 sulfate? I'd get a different ratio. Or, what often happens when you're combining big chains of carbon, that they can go together in different ways, and they do. They go together all the ways you can. Okay? So that you can't make just the one shape you wanted. An example. So if you have a pen, you can write on the board. Okay. So if I take this chemical and I add a Cl to it, it can come together in 3 different ways. It could make that, where the 2 Cls hook on to separate chlorines, or it could make that, where they hook on to 2 different carbons, but now they're across from each other. Remember, double bonds don't rotate. So this is different than this. Or they can come together like this, where both chlorines add onto the same hydrogen. All 3 of those are possibilities. When you mix them together, you can't control which one it does. So if your goal is to get the one that's nonpolar, this one, your percent yield is not going to be 100%. Does that make sense? Because it's going to make all 3. You can't control which one it makes. So you're not going to get 100% because you're going to make some side products, things you don't want. Okay? So what you do is you make this whole mixture, and this is polar because the chlorines are on one side. This is polar because the chlorines are on one side. This is nonpolar because the chlorines cancel each other out. So what you can do is mix oil and water together, pour the stuff in, shake it up. This will go into the oil. Those 2 will go in the water. Polar dissolves in polar, nonpolar dissolves in nonpolar. And then you take that nonpolar liquid and evaporate it. And that's how you'd isolate it. You could get just that one kind, but it wouldn't be everything you made. So you'd be less than 100%. Would it be your fault that it's less than 100%? No, you didn't do anything wrong. That's what happens. Okay. Now, in actuality, this is one of the ways that people get their graduate degrees. Okay, bachelor's degree, you have to prove that you've learned what you were supposed to have learned. A master means that you have added to the knowledge of science, that you have done some original research. And one of the common ones for chemists is to try to improve the percent yield of a reaction. They'll examine a reaction that's got a low percent yield and say, what can I do that would make it so that it makes more of that product? How can I change it? So they'll take a reaction that gets a 30% theoretical 30% yield and find a way to get it up to 50%. And they'll have to talk about why. They'll have to know why. You can't be just, I'll just try this and see. You gotta say, the science says this should happen. I tried it and I got a bigger percent yield. So when you want to do this reaction, don't do it that way anymore. Do it this way. And so science improves because they get their chemicals more efficiently, and we understand how things bond better. Make sense? So so it's not always your fault that you don't get 100%. PhD is it's got to be again more new stuff. I'm usually on a bigger scale, a bigger idea. So one small experiment is too small for a doctorate. A doctor means you got a big, broad body of knowledge. So for that, you have to come up with original research, and then they bring you in front of a room where people are experts at what your research you're at, and they ask you questions, and you have to defend your research. You know, how do you know that? How do you know that that's what you know? You know, so that's how you get your doctorate, your PhD. Okay. So, student reacts 5 grams of magnesium with an excess of oxygen to produce magnesium oxide. I shouldn't even told you that to produce magnesium oxide. Darn it. Okay, the student finds that the product weighs 8.10 grams. What is the percent yield? So, percent equals actual over theoretical times 100%, right? So, I need the actual. So, am I supposed to go burn some magnesium? Nah. Student did it. The product weighs 8.10 grams. How are you going to find out the product weighs 8.10 grams? You're going to actually weigh it. You're going to make it and weigh it. So that is my actual yield. What about the theoretical yield? Can I just put that 5 grams there? No, because that 5 grams is magnesium. My product is not magnesium. So I got to figure out how much I could have made. So I want to get rid of grams of magnesium, change it to moles of magnesium. And 1 mole of magnesium weighs 24.31 grams. And then I want to get rid of moles of magnesium and change it to product. And they said the product was magnesium oxide. And I'm stuck. Why am I stuck? I get those numbers from the balanced equation. Something's missing here. A balanced equation. So that is Mg plus oxygen. Oxygen is going to be O. Does Mg get a 2? Does O get a 2? And what's it going to make? 2 elements is the combination reaction, so it's going to be MgO. Oh, they told you it was magnesium oxide, but they didn't have to. There's only one product possible. And then I balance it to get my 2 O's. I got to put a 2 in front of MgO, which gives me a 2 in front of Mg. So I put a 2 and a 2 here. And then I get rid of moles of MgO, change that to grams of MgO. So 24.31 plus 16.00 is 40.31. So 5 divided by 24.31. I'm not pushing times 2 divided by 2. Times 40.31 equals, I get 8.29 grams of MgO. And that is my theoretical yield. Times 100%. And I get it's 97.7%. This went pretty well. Maybe you lost some up in smoke. The only variation I can think of on this, if you'd had a lousy percent yield, what if they had gotten 45.2% yield? How much product would they have made? Well, now I know 45.2% equals how much they would have actually made. That's what I'm looking for. Over the theoretical, which we just said was 8.29 grams, times 100%. So really what I'm going to do is I'm going to take 45.2% of 8.29. That make sense? So I'm going to divide by 100 to get my 0.452. I'm going to multiply both sides by 8.29 grams. I'm going to get that was what my actual equals, which is 0.452 times second answer equals 44.2. No, 0.42 for that. No, 0.452 times 8.29 is 3.74. So instead of making the 8.10, he would only made 3.74 grams. Things went badly for him, right? Hey, had a chance to practice that tonight, and we will move on tomorrow. Reach our